Hello friends, I welcome you in lecture number 10 on set theory. In this lecture we are going to discuss some basic set identities. So sets under the operations of union, intersection and complement satisfy various laws or identities, which we are going to discuss one by one in this lecture. So first of the identities which we are going to discuss represent idempotent laws. So idempotent laws are represented by these two identities. If A is any set, then union of A with itself is equal to A, and similarly intersection of A with itself is also A. Now all the identities which we will write can be written. If we know the one identity, then another identity can be written by replacing union operation by intersection, and if we have universal set, say U, then that will be replaced by empty set. So this is known as principle of duality. Here we have union of A with itself, so other identity is written by replacing union by intersection, and we keep set A as it is. So we will keep in mind that all the laws which we are going to discuss will be in pairs, and if we know one of the identities, then other identity can be written by replacing union by intersection and universal set by empty set. So we will remember that these two identities represent idempotent laws, that is union of A with itself is equal to A, and union intersection of A with itself is also equal to A. So to prove this identity, we know that two sets are equal if one set is subset of another set. So to show that these two sets are equal, we must show that A union A is subset of A, as well as A is subset of A union A. That means we must show that every element of A union A is also an element of A, and vice versa. So we start by taking X in the union of A with itself. So X belongs to A union A implies, by the definition of union, X is either in A or in A. So this is equivalent to the fact that X is in A. Now if we go in reverse direction, then also all the implications are correct. If we start with X in A, then we can write this as X belongs to A or X belongs to A, and this implies X belongs to A union A. So if we take X in the A union A, then X is in A, that means A union A is a subset of A. And if we start by taking X in A, then also we find that X is in A union A. So both the sets are subsets of each other. Therefore A union A equal to capital A. Similarly, we can prove this identity A intersection A equal to A. So we start by taking X in A intersection A. By the definition of intersection, X is in A and X is in A, and this is equivalent to fact that X is in A. Similarly, if we start from this step, then X belongs to A implies, we can write in this way also, X belongs to A and X belongs to A, and that implies X belongs to A intersection A. Therefore A intersection A equal to capital A. Second, identities represent associative laws. So if we have any three sets A, B and C, then A union B in the bracket union C is equal to A union in the bracket B union C. So here we are combining two sets A and B, and then we are taking union of A and B with union C, and here we combine B and C first, and then we take its union with set A, and this identity says that these two are always equal. And other identity can be written by replacing union by intersection. So here this union is replaced by intersection, this union is also replaced by intersection. Similarly here we write intersection. So this also can be proved easily. We have to show that these two sets are subsets of each other. That means every element of this set is also an element of this set, and every element of this set is also an element of this set. So we start by taking X in the union of A union B and C. This implies X is in the union of A and B, or X is in C. Now X belongs to A union B implies X belongs to A or X belongs to B, and we keep this as it is. Now this whole thing we can rewrite as X belongs to A, or in the bracket X belongs to B or X belongs to C. Now this implies X is in the union of B and C, and X is already in A. This gives me X must be in the union of A and B union C, and we can easily check reverse implications are also true. Therefore both the sets are subsets of each other, and this associative law hold. Similarly we can write for the intersection. We start by taking X in the intersection of A intersection B and C. This implies X is in the intersection of A and B, and X is in C. This implies, from this we can write that X must be in A and X must be in B, and X is already there in capital C. Now this whole statement can be rewritten in this way. We consider X belongs to A, and we combine X belongs to B and X belongs to C. This means X is in the intersection of B and C, and X is already in the set A. So this implies X is in the intersection of A and B intersection C. Similarly we can check the reverse implications, they are also correct. Therefore intersection of A intersection B and C equal to intersection of A and B intersection C. So these are the associative laws for union and intersection. These two identities represent associative laws. Next laws are commutative laws. So this is very familiar property. We know that union of A and B, that is A union B, must be equal to B union A, and similar property holds for intersection. A intersection B and B intersection A are always equal. Proof is easy. We start by taking A union B, that is the set of all those X which are either in A or in B. Now this we can rewrite as X belongs to B or X belongs to A, but this set is nothing but B union A. Therefore we have shown that A union B and B union A are always equal. Similarly we start by considering A intersection B. So by the definition we consider those X such that X belongs to A and X belongs to B. So this statement we can rewrite as X belongs to B and X belongs to A, but this set is nothing but B intersection A. Therefore A intersection B and B intersection A are always equal. So union and intersection satisfies commutative laws. Next laws are distributive laws. they are represented by these two identities. Here we can say that the operation of union is distributive over intersection. A union B intersection C equal to A union B intersection A union C. And another property can be written by replacing union by intersection and intersection by union. So here I have union, so that I replace here by intersection, here intersection, so we write union. Similarly, union is replaced by intersection, intersection is replaced by union, and union is replaced by intersection. So we remember only one identity, other identity will be obvious. What we have to remember is intersection is replaced by union, and if there is universal set, then that will be replaced by empty set. So we can prove one of the distributive laws. Suppose we try to prove this first one, A union B intersection C equal to A union B intersection A union C. So we first take any element in this set. X is in A union B intersection C. So by the definition of union, X is either in A or X is in B intersection C. Now we keep this as it is, and because X is in the intersection of B and C, we can say that X is in B and X is in C. Now this statement we can rewrite as, first we consider X belongs to A or X belongs to B, that we consider as one statement, and X belongs to A or X belongs to C, that we consider as another statement. So this statement can be rewritten in this way. Now this implies X is in A or X is in B, that means X is in the union of A and B, and X is in A or X is in C, that means X is in the union of A and C. And because of this and, we can say that X is in A union B intersection A union C. Now we can check reverse implications also. Suppose we start from last step. Suppose we consider X is in this set, then this implies X belongs to A union B and X belongs to A union C. So this statement implies this statement, so we can write double implies here. Now X belongs to A union B implies X belongs to A or X belongs to B, and as it is, X belongs to A union C implies X belongs to A or X belongs to C. So this statement implies this statement. Now this whole statement can be rewritten as this statement, X belongs to A or X belongs to B and X belongs to A or X belongs to C. So we can see we have X belongs to A or X belongs to B and X belongs to C. So we can write that this statement implies this one, so we have double implies here also. Now this statement implies X belongs to intersection of B and C, and we keep this as it is. So this implies X belongs to A or X belongs to B intersection C, and due to this or sign, we can say that X is in the union of A and B intersection C. So both the implications are correct in both the directions. So if we consider any element in this set, then it is also present in this set, and every element of this set is also an element of this set. Therefore we have proved this property or this laws, which is known as distributive law. Next, identities represent identity laws. So this laws says that if we consider union of any set A with empty set, then we will obtain set A back, that is A union empty set is set A. Now this law is written by replacing this empty set by universal set. This bold U represent universal set. So here we keep A as it is and union is replaced by intersection, empty set is replaced by universal set, and we obtain this identity law A intersection universal set equal to A. Similarly, another identity law is union of A with universal set is obviously universal set, and this is written by replacing union by intersection and this universal set by empty set at both places. So these are very obvious laws. We can see, we know that empty set is always subset of any set. So therefore union of A and empty set must be equal to A. Similarly, for this we can justify in this way, because U is a universal set, A is a subset of universal set. This means intersection of A with universal set must be equal to A. And because A is a subset of universal set, union of A with universal set must be equal to universal set, which justifies this law. And because empty set is a subset of any set, if we consider intersection of any set with empty set, then there will not be any element which is common to both the sets, because empty set has no elements. So this is also obvious. Intersection of A and phi is always phi. So these are the identity laws. Another important laws are complement laws. So suppose U is universal set, A is any subset of universal set, then union of A and its complement must be equal to universal set. And if we replace union by intersection, here we have to replace universal set by empty set. So intersection of A with its complement is empty set. Similarly, complement of universal set is empty set and complement of empty set is universal set. So all these laws, complement laws, are obvious using the definition of complement of a set. So we are not writing their proof. And the last law which we are going to discuss in this lecture is complement of a complement of A must be equal to A, where A is any set. A dash means the set of all points which are not in capital A, and we are considering complement of A dash. That means we have to consider those points which are not in A dash. So the points which are not in A dash must be in capital A. So complement of a complement is equal to set itself. So this law is known as involution law or complementation law, and these laws are known as complement laws. So in this way we can easily write down set identities. If we know one of the two identities, we can write other identity simply by replacing union by intersection and universal set by empty set. So we stop here. In this lecture we have discussed some of the basic set identities. In the next lecture we are going to discuss some other important set identities. So I hope you like this. Thank you very much.